The IPCC did a range of scenarios, high emission scenarios to low emission scenarios. So what could you do if you capped your emissions, or what if you did, what would happen if you let them go? And this six model ensemble, if you like, sort of reflects the high level of where temperature is expected to go if we didn't do anything, versus if we did everything we possibly could, we may be able to keep it around about the 2 degrees. The consensus now in the 2007 report was basically that we'll get round about that 4 degree mark, which is a substantial shift in temperature, and the consensus seems to be settling on that. If we have a look at real data, and here is the global mean temperature through time, you can see the blue line and the black dots reflect the temperature of the globe throughout times from the 1840s, 1850s, and you can see though that the lines that are indicated there, so there's a red line showing the average of the lot, and then the last 100 years, which is the purple line, and beyond that is the last 50 years, is the orangey line, and the last 30 odd years is the yellow line. The point to take away from it is that's real data, and it's showing that the temperature is rising through time, but not only rising through time, the more recent trend is for a very rapid increase. Stern, an economist in the UK, decided to have a look at some of the implications of climate change from an economic point of view. He brought together the biological systems data and then overlaid the economics and some of the implications of temperature changes of 1 to 5 degrees. The broken yellow line reflects intermittent, fairly substantial events. The solid yellow line represents continuation of stress, and the red means extreme problems for those sectors. The sectors that he looked at were food, water, ecosystems, and included 2 others. Because we're outside the bounds of where we've been before, the probability of extreme weather events and the risk of abrupt and major irreversible changes need to be factored in, and he felt that they were very substantial economic drivers of the globe. ABARE provides us a bit of an insight as to where the fuel and energy consumption of the globe is headed, and you can see out to 2050 from everything from the non-hydro renewables through to coal, where the demand based on population projections is likely to be. So we can be fairly confident that CO2 is likely to continue to rise. Now, the implications of temperature change are more evident in the extremes. So in this case, a single heat wave event in Western Europe, noting that South Australia is 39 today, that event where most of the houses are designed for heating, not cooling, they lost 45,000 people. But when they analysed that event, they found that it was 3 times as more likely to have occurred, and that by 2050 it would be an everyday event, and beyond that it would be a cool event. So let's have a look at that data. And we can see here that the red lines are the actual data. You can see that single heat wave event. The blue line is the projected moving average of temperature into the future, and the black line is the model into the future. And you can see if you extrapolate that across, by 2050 it's an everyday event, and beyond that it's a cool event. So there are concerns for the implications of temperature on health. How good is our modelling? Well, this little graph shows you that if you only look at the natural occurrence, the model data, which is the blue line, so natural, which includes volcanic and solar, versus the observed data, so the actual data, separate around about the 60s. If you add the anthropogenic, a buzzword for greenhouse gases and sulfates, you find that the two then start to correlate. So there's a fair degree of confidence that not only is the hypothesis correct, but also the modelling is shown to be improving in its quality and accuracy. Many people thought that CO2 as a fertiliser would just result in increased growth of the rainforest, but a 20-year study in the Amazonian rainforest found that all the long-lived perennials died or were thinning out, and the short-lived ephemerals were increasing quite rapidly in their density. So the saviour of the rainforest in sequestering carbon is not all that well placed. The implications for Australia now, we'll cut back to Australia, is a very substantial statement which doesn't have a lot of impact for you out here all the time, but it does have a major bearing on the more easterly seaboard of Australia. And the International Panel on Climate Change in 2001 and 2007 reaffirmed the fact that the El Nino events are going to become more common and more El Nino-like mean conditions may prevail in the future. I'll talk a little bit about that. Rainfall variability, we have one of the most variable patterns, and Mike alluded to that earlier, in the globe. And that was one of the reasons why Australia has been so recalcitrant in taking any action on climate change, where many of the European countries have moved very rapidly because of their stronger and far more predictable rainfall patterns. Where does that hub of variability sit? As indicated by Mike correctly, it's largely where we sit here today, but Queensland is a strong node, and Charters Towers is the nub of the problem. The only place that's more variable is the poles. Having a look at some real-time data, variability has increased by about 25%. Now that's variability in rainfall, both intensity and the duration, and the gaps in between it. So the variability has increased quite markedly, and that's a particular point to note when you start to look at the pastoral sector. So they are very substantial changes. That graph reflects a period of time between 1900 and 1950 and from 1950 to 2000. But that variability in terms of measured, actual, real data has shifted by 25%. We know also that Australia's temperature is rising rapidly. The black line in the middle is the 1961 to 1990 baseline. So hence obviously before then it was cooler, and now it's well and truly above that. So you can see that by just using that baseline you can see a rapid rate of increase marked and evident by the black line where the temperature has increased by between 0.8 and 1.3 degrees depending on where you sit in Australia. That might not sound a lot, but when you start to talk about the numbers of days of extreme, you'll find that that's quite marked. Sea levels are rising quite substantially. Now in this case the axis is about millimetres of rise, and they are millimetres, so they're only little, but you can see since 1990 until 2006 it's risen by about 40 odd millimetres. That's a very substantial shift, a very substantial shift. The difference between the red and the green is just a change of satellites, where one satellite was transitioned into another one. I spoke about these El Nino Southern Oscillation Index, the El Nino phenomena. This is largely and best explained by sea surface temperatures. When there's an upwelling of blue water, indicated by, in this case, cool water, only by a degree or two, in the eastern equatorial zone, and an upwelling of warm water indicated by the red on the eastern seaboard, this is a classic La Nina event where we get fairly substantial rain on the eastern seaboard of Australia. Now the interesting thing is more to do with how it drives the pathways of cyclones. If we have a look at the reverse, the classic El Nino, and this is where they refer to an El Nino-like mean state condition, and that basically means that the water, the red warm water, in the eastern equatorial zone doesn't change, and so you get the rain or the cyclone patterns move out to sea and fall over Fiji instead of on eastern Australia. The upwelling of the blue water on the eastern seaboard means that the low pressure systems and the high pressure systems on the eastern seaboard of Australia and the cyclones track out to sea. But we'll have a look at that in a minute. There's just an example of the sea surface temperature average for September. We know that the El Nino Southern Oscillation Index is obviously well or reasonably well linked, but it's not a strong predictor of climate in Australia, but it does provide one of the core indicators of when major substantial wets or dries are likely to occur. And this little graph just reflects the actual data, which is the black line flowing through it. The red coloured in areas are the times that we've had extreme drought, and the blue areas of the time when we've had very good rainfall. And many of you would remember those early 70s or mid 70s and the early 90s, or late 80s, early 90s.